sample problem 14. This sample problem is pretty much the same as the previous example, but I purposely made the directions favor the negative. And there's a reason for that. Many students still struggle with the idea that positive and negative in physics is only about direction and not necessarily speeding up and slowing down. And let me show you what I mean. So we have a 2 kilogram block and it's being pushed towards the west. To the west with a force of 15 newtons against a frictional force of 3 newtons. And this is where so many get hung up. The friction opposes whatever motion you have. Since we're pushing the block towards the west, this means that the friction is doing the opposite of west, which is north. I mean, not north. I mean east. Oh, good gravy. So the block is being pushed towards the west, but the friction is working in the opposite of west, which is east. It seems weird, but your friction is actually going to turn out to be a positive vector. And again, positive, negative in physics generally just means direction. And of course, the block is being pushed for 2.50 seconds. Okay, so then the block is allowed to slide on its own. Section B happening here until it comes to a complete stop. Just so it really is basically the same thing that we just did, but the directions are kind of opposite to the way we had it set up before. And of course, we're looking for the acceleration of the block during the push, the distance or really displacement during the push, the final speed during the push, and then the acceleration when it's sliding on its own. But this time we're looking for the time it takes. So instead of looking for the displacement like we did in the last question, we're looking for the time. Nothing really changes, the exact same technique that we did before. We just got to keep our positives and negatives straight. Okay, so a quick look at the givens here. As you can see, the mass of 2 kilograms, it's the same for both sections. In part A, our push is to the west, friction is going to be to the east, and our VA1 equals 0 meters per second. That is a necessary assumption because we weren't really given that information explicitly, but we likely won't be able to solve the problem without this particular assumption. And we know the time is 2.50 seconds. And that, of course, is for section A. And focusing on section B, we know that the push is gone, so it's just the force of friction that remains. And we know that the speed at the end of section A is equal to the speed at the beginning of section B, or really velocities. Summarizing what we're looking for the acceleration in section A, the displacement / distance in A. We're looking for VA2 / VB1, which is the same number. And then we're looking for the acceleration in section B and the time for section B. So drawing a free body diagram for section A, note that FP is larger magnitude than the force of friction. So therefore, we should expect a negative acceleration in this case. And once again, we do not have enough kinematics information to solve for the acceleration in section A because we only have VA1. And again, that 0 meters per second was an assumption. And we have the time. So we must look towards dynamics again. And as a reminder, the normal and the gravity do cancel each other out. So what's really only at play here is what's happening along the x-axis. So we can just focus on F net AX. So F net AX is equal to FP plus the force of friction. Dropping the vector notation, we get negative FP plus the force of friction. And again, the negative means that the push force is to the west, the friction is to the east, and we're replacing F net with mass times acceleration in section A because that's Newton's second law. And again, no subscript on the mass because it's the same mass for section A and section B. Isolating for the acceleration in section A, we divide both sides by m, substituting in, and we get an acceleration of -6 meters per second squared, or 6 meters per second squared towards the west, which is expected because the push overwhelms the friction. Now, using that fact, we do have the acceleration for section A now. We have VA1 and we have the time. Therefore, to find the displacement in section A, we can use equation number 2 from our kinematics formula sheet where we don't have VA2, and that is the only formula that is relevant. Substituting in, we get negative 18.75 or 18.75 meters backwards, except that should be recorded as 3 sig figs, not 4. So as 3 significant figures, we have to round that 5 off, and that is the terminating 5 rule, which means that that 7 turns into an 8. There we go. Better. And also, how about west? As you can see, when I solved these last time, I was in a bit of a rush. And you can see all those minor little mistakes that you make. That's why proofreading's important. Should take my own advice. Part C, we're looking for our VA2/VB1. I'm actually going to change my color coding on this, and I'm going to change it to the dirtier of the ambers here. It's almost on brown here. So this here we found in part B, but this result here was based on a found value. So again, because we found this result based on a calculated result, this one even has more potential for error in it. Hence, DA is the one that's subject to the most amount of error. VA1 and TA have no error at all because they're given, and acceleration A has a smaller potential for error. Therefore, when we're looking for our VA2, we should avoid using our DA, which means we should use VA2 is equal to VA1 times the acceleration in, good gravy, let's be more consistent there, the acceleration in section A times the time in section A. Substituting in, we get negative 15 meters per second. Therefore, VA2 is 15 meters per second west. And that also means that our VB1 is 15 meters per second to the west. Now, solving for the acceleration in our section B. So we now have, again, a new list of kinematic information. And I transferred over the VB1 calculation from section A, because VA2 is equal to VB1. Of course, here we only have two given pieces of information. We still have insufficient information to solve for the acceleration in section B. Therefore, we look to, once again, dynamics and putting the subscript on the force of gravity. Once again, the normal and gravity cancel each other out, so they are not relevant for our acceleration. So we can just focus on the x component of the forces. In this case, F net bx is just equal to the force of friction, but the force of friction is in the positive direction because it is pointing towards the east. Isolating for acceleration in section B, we divide both sides by the mass. We get positive 3 divided by 2, which gives us positive 1.5 meters per second squared, or AB is equal to 1.5 meters per second squared in the forward direction. Except it wasn't the forward direction. Let's be consistent. It was east. There we go. And now finally, solving for the time in section B. So now we have our VB1, our VB2, and our acceleration, and we're looking for time. So we're going to, I think this version of the formula, equation 7 from the kinematics makes the most sense because we can isolate for the time really easily. This step here, I want to be followed up with that one there. I want you to show me this step here and don't just jump to this line here because this is frequently the mistake that students make. The delta means VB2 minus VB1. Often students will just write, because they know one of them 0, they'll get the negatives wrong. So I would like to see you write VB2 minus VB1 and then substitute your 0 minus negative. And this negative business turns into a positive, which is important because if you don't do it that way, you run the risk of getting a negative time, which one cannot just have. Okay, so therefore our time for section B is 10 seconds. So again, not really that different from the previous sample problem, just you have to be comfortable with the fact that friction can be positive because it's really just based on its direction.